Here we are. Yes, audio is there. Waiting for my folks to appear. Well, anyone did the exercise? Anyone succeeded? Excellent. We have 1. Excellent. Very good. 2. It's already comforting. Now, before going to the solution, I discovered that there was some little issues while I was coding, so probably there is some variable to be adjusted. So I will compile, and it will tell me, class ICP does not have any field name _3. It's true because it's called KD3. Try again. Okay, and it goes through. So, all right. This was one mistake of mine. All right. This mistake was because in the class ICP, I called the 3 KD3 and not _3. Okay, how do we proceed? We loop through all the points. Fine. A very first thing we might want to do is to clear the vector of correspondences, because at each iteration, this is our output. So at each iteration, we're going to reuse the same variable, so it's sensible to say clear the iterations. We're not doing actually any memory allocation or thing, because we said the system at the beginning on constructor, hey, please reserve in the correspondences at least this number of elements. So it will only add to the set and adjust some counter without stimulating the heap. Right? And then at this point, what do we need to do? We need to calculate, apply a transform to the moving point in order to determine the query. Or M prime. Third action that we need to do a search in the KD3 around query. In the class I have put, the result, I recall, we are interested in finding the best, so let's see what was our interface of KD3. We had many methods, and the method that we liked was either best match fast or best match full. And either method takes as input a point, which is the query, and returns, if possible, a pointer to a point. Null pointer if no point is found, and norm is the parameter that we pass to the function that defines the size of the ball within which to search. So we're gonna use this fantastic method. Point type is vector 3f in our case. And then here we would need the radius of the ball to search. Here I could just either write an handcrafted value or use a parameter that I put in the class. ICP.h, which I think I put ball radius. So I will reuse this ball radius over here. Okay. If I don't find a point, I don't need to do anything. It's not break, it's continue, because we're gonna restart the loop from the next iteration. Point pair, and point pair takes 2 inputs. The first input is a fixed and the second input is the moving. And it takes not a pointer, it takes a reference. So I'll have to pass here the referencing f, the pointer to f, and query. Or if I want to be consistent with the slides, m prime. Will it work? Who knows? No. Let's block the description, compile. No match. It's not m prime, it's f. F, and this is m prime. Renaming issues. And it went well. Now what is, now we need to test it. And then how are we gonna test it? I built a main. I an ICP test. Okay. How does this main work? Well, first it reads from the command line. To read from the command line, actually the C runtime is gonna fill these variables out of the arguments that you put in the command line. argc is the number of arguments that you write after the command, and argv is a array of strings, basically, that contains the arguments. The first argument is the I could also write argc of 0. The first argument is the name of the program, and then argument 1 is the first argument, argument 2 is the second argument, and so on and so forth. So what is this program doing is taking this number of arguments, a translation on the x, a translation on y, and a translation on a z, and 3 angles, rotation on x, on y, and on z, and the number of points. And it reads them from the command line. But these are strings, so the very first thing that you need to do is to convert a string to a float. To this extent, we will be doing atof function, right? The number of points is integer, so we will convert it with a to I. So we need to declare a bunch of floats, and we need to declare number of points. Once we have this read the command line, the very first thing that we do is that we generate n random points. Now we generate a container, container type, which is a vector 3f vector, having a certain number of points. Then we iterate on this element of this vector, getting them by reference, and assigning to each point a randomly generated vector, and then scaling it, because it's between -1 and 1, or between 0 and 1, the elements. We would like to have something bigger, so we zoom it to 100. So it's like multiplying vectors by a scalar. And this is our main. But in order to test ICP, we need to take a cloud, and this container, these KD points, which I call here, like, let's say, fixed points. Is the points of my machinery. And fixed. right? Then the second action is to construct a transformation matrix, so a pair rotation matrix and translation vector that then we will put into our isometry. Remember that the field linear of the isometry corresponds to the rotation matrix. The field translation corresponds to the translation vector. And then I have a simple utility file called rotation that basically constructs C robotics 1 constructs even an angle, constructs a rotation matrix on the x, a rotation matrix along the y, and a rotation matrix along the z, right? So this is the meaning of this file. So we assign to the rotation matrix a rotation matrix on x of alpha x, a rotation matrix multiplied by a rotation on the y, multiplied by the rotation on the z. And then we assign to the translation the three fields that we have read here. Okay? At this point, to test our ICP, we need to apply this transformation to the points. So we declare another container, which is constructed from the previous container. So this is going to make a deep copy of everything. And then we go through each point of the out of V transform points. For each point within the transformed points, it applies this transformation. Okay, by multiplying the point times the isometry ISO, no, by the point. And then we instantiate our ICP and we run it for 10 iterations. We instantiate is not KD point. This is transform points. No, sorry, fixed. And then let me call the other transformed points moving points. I think I like it more. And this 10 means allow a leaf to contain at most 10 points. Okay? What we are going to expect to see? Well, if you go to ICP, what I can do also for fun is to print the transform that we input. And then at each iteration of ICP, I can also print the transform that is being estimated at that step, together with other parameters. So I go into the optimize business, eigen ICP, CPP. Okay. Some sugar. argv of 0. Okay, KD points, this is me renaming the stuff. All right. Let's see. All right, so that's what our program prints. This is the transform that we're looking for, right? And this is the transform that is being estimated by our program during the different iterations. So this is our input, basically, that the program doesn't know because we're just like taking one cloud and modifying it originally. Then here we start with the iterations. I think. And this is the, oh, maybe I could print the transform on the step before. Let me do this. Transform before. I want to show the transform before and after. No, it's not what I want to do. I'm now instrumenting the program to print the transform before and after the optimization. No. I just want to see. So this is the number that I would like to reach, and the numbers that are here are non-relevant because they are not going to be used during by the system anyway. All right. I know it. Sorry, 1 second. Yes, this one over here. Now I want to go to the test. The test, yes. I will explain you this in a second. So, like, what I would like to see is that the keys that at the beginning, yes, at the beginning I have a transform. Reset. Sorry, I reset. Okay. Come on. At the beginning I have a guess transform, but my initial iteration starts from the identity. At the first step, I get this correction, right? The system also tells me you have 39 points that I have found, and the sum of the square distance of these corresponding points is that much. All right. Then we proceed with another round, and the system finds 97 correspondences, meaning that that was a good step. We clearly start from the transform, which is the transform before, but then we refine it a little bit, and then we reach this situation. Then we go at iteration 2, and then once again we start, and then the situation is improved because we see that before I have found the beginning I found 38 correspondences, then 97, and then 100. What does it mean finding a correspondence? Remember that when we do a nearest neighbor search, we stop in a ball. And so finding only 38 correspondences means that there are only 38 points out of these 100 that I have selected that fall within the ball of one radius from the query. Kernel is something which is C probabilistic robotics, and then chi-square, blah, blah, blah. Then now, here we are reaching a horrendous convergence, because we see that we have found 100 correspondences, and we have this error of this is the sum of the squared distance between corresponding points. So we are below 1 centimeter. At the next iteration, probably the key will be something to the minus whatsoever, and the transform will be quite close to the final one, right? Let's see, this is the final one that we find, the final transform. So it's, and then I will just now copy, for simplicity here, the transform that we had to find, right? Yeah, it's horrible, but it works. So 099903, we have it. 099347, we have it. 099 blah blah blah, we have it. Here we have 0.1. Remember that we are working in floating points, so this is basically 0.1. This also is basically 0.1, which is this other element. And so when you read to the minus 9, you read 0. So like basically we have found a perfect transformation with our simplistic mechanism. Now, in doing the test, I made a black magic because I flipped, according to our signature, I flipped fixed point and moving points. But if I Google in the class, in the header file, rp eigen icp.h, I figure out that here I have to give fixed and here I have to give moving. Okay, this is a magic of the way I have constructed the optimization, that actually it calculates the position of the it calculates not the direct position, but it but it calculates the inverse position. It's like a matter of optimization. Okay, so like by flipping the 2-point clouds, instead of calculating the direct transform, I calculate the inverse transform. Alternatively, I could do, because these are the moving points seen by the fixed. Alternatively, I could also do something even more dodgy and say never do this in a program. I just swapped the two sets and then I'm initializing the points with the inverse of the other. But that's no. And that basically finds the very same result. But anyway, this is a detail of ICP. The task of this exercise was simply to show you that you can construct something like reasonable. Now let's try to stimulate our program and to give it a little bit worse initial conditions. So 1 meter in translation, and let's see what happens. So here we are giving 1 meter in translation on the x, on the y, on the z, and the rotation on the x of 0, on the y of 0.1 radians, which means 5 degrees, and on the z of 0.1 radians. Let's see what happens. What happens? It happens that it converges. How do you see it? Well, I see it from here. Because the chi-square is very limited. But let's make the situation even uglier. Let's add 1,000 points. Now, by adding more points, what happens in this case is that you make the thing more confused, because there will be many points which are close to each other. And when you have such an initial guess, it's very, very likely that you're going to stick with a point which is to have a wrong correspondence, right? And what I expect is that now it will not work as well as before. Let's see what happens. Yes, we have substantial chi-square error. So now the transform that we have found is not as nice as the one that we were finding before. But this is not a problem of the implementation, this is a problem of the algorithms. There are plenty of ways, in case you want to register point clouds, to make it much more robust. And they involve using different metrics for finding the heuristics, calculating a normal of a point, using different ways of optimizing, but this is definitely out of the scope of robot programming. Okay? Now, we have tested it, we have seen it, we played with it. I'm gonna commit the solution for those that didn't complete the exercise, and I'm gonna present you the other part of the exercise. Meanwhile, if you have questions, please write them in the chat. Okay, I've just pushed the exercise in class folder, and now we're going to the second part of this task, which will be entirely devoted to you. So now, me on YouTube, I will explain you the task, and then I expect you to do it. Take your time. I will then close the streaming and then open a Zoom broadcasted by email, so that I can respond to individual questions and follow each and every one of you. All right. So now, first I present the exercise on YouTube, so it stays, and then we go to the interactive part. See, never know. All right. Now, that's the exercise. So you have to do whatever we have done in 3D, but you have to do it in 2D. Okay, that's the game, and using as a container a list instead of a vector. This is what I want you to do. You can clearly now take free inspiration from the 3D version. In addition, in this implementation, I've given you for free Eigen ICP optimized correspondence. I've given you for free the optimization part, that you don't have to do much. And I will also start filling something, right? Because I will also start putting in the variables that are required by me for the optimization, because otherwise you start complaining that it's not doable. So kernel key, only kernel key. We have key square sum and kernel key. Key square sum and kernel key, and also yes. These are just variables that are float that are served to support the optimization. I think dx, well, on this. Okay, the rest is up to you. Let's see if it compiles. I drag in the optimization. No, I can't. No, it's up to you. So like what I want you to do is to construct an ICP working on 2D. Of course, you have a test program because you have it. Eigen ICP 2D test.cpp. It's here with everything there. So you have your test program, but I'd like you to write, starting from the H, I just partially compiled it by putting variables that I did not explain. And you can start putting in the thing. I recall that I've given you the optimization that is in this file over here. That is a separate piece of program. Okay, guys, is that clear what I'm asking you? So we have seen the complicated part. Now you do the simple part. And in addition, I'd like you to use as container type a list instead of a vector. Now, if there are generic questions, please write them on the chat, because in the next 2 minutes, I'm gonna open a Zoom link, and I will send you via email the Zoom link of the session. Of course, the Zoom will be recorded as well. No questions asked. I'll wait 2 minutes, and I push this object. So no questions, then I don't know, my system will crash if I try to open Zoom and OBS at the same time. So in the next 3 minutes you will receive an email with the Zoom link. Have fun, ciao ciao.